Good afternoon, everyone. As Dr. Morini mentioned, today I'll be talking about the architected polymer reinforced cementitious composite. This is basically a prequel to what my advisor presented earlier this morning. I need to refer to that presentation a couple of times. But basically, this is going to be the outline of this presentation. I'll start by introduction, background, and then I'll present research methodology and the results, and furthermore, I'll summarize the list of results and conclusions. So basically, I'm going to start with the same argument that Dr. Farnham presented. So we know that in order to increase the tensile strength of concrete, we've been using rebars, longitudinal rebars, and they're primarily manufactured with steel. And this is an example of a conventional layout of reinforced rebar that we've been using in the field. And their main advantage is that they provide some more toughness, strength in order to prevent catastrophic failure. Here the questions we're asking is that are there architectural elements that we can find in nature to get inspired by that can provide a better or a comparable mechanical advantage to our system. So basically the nature-inspired architectures that we looked into started by architectures at micro level, like the bulligand or alternating layers that we find in crustaceans and also in nacre. And furthermore, which is mainly the purpose of this presentation and this part of our research, we looked into macro architectural elements such as honeycomb, which has a sandwich effect, interlocking effect, and provides good compression, and also later on plant stem architectures that have tubular and hollow structures within them and provide good flexural rigidity. So based on that, in this presentation, we're going to first start by talking about the mechanics of the reinforcement design in order to first establish how we're going to come up with a new layout based on the architecture we use, and before that, based on the material that we're going to use. So as I mentioned, we are trying to increase the tensile strength mainly with the reinforcement. So in order to do that, we also need to know the tensile strength and properties of our reinforcement. And in this case, the reinforcement is going to be a 3D printed polymer. So we used a simple uniaxial tensile test accompanied by DIC in order to capture the full stress-strain behavior, which we further used to come up with the mechanics and the design of the reinforcement. So we started by working on different filaments in order to find which one would be best in order to start playing around with the architectures that we want to use. And surprisingly, the filaments that were not reinforced with fibers showed a better overall tensile behavior. And the reason for that was because of the defects that we were getting through the process of the manufacturing, 3D printing of the filaments. So we chose PLA for that purpose, and furthermore, we just started working with that in order to print our reinforcement. But before going into the macro architecture, we started some initial studies on different microarchitectures. Here I'm not going to go deep into that, but basically the reason for that was to figure out which printing pattern we're going to choose that would provide us with the best mechanical properties for our reinforcement. And based on that, as again my advisor mentioned earlier this morning, we followed a path to get to the different mechanical parameters of designing our reinforcement. So basically, based on the ratio of the strain of our different materials, which in one hand we have the polymer reinforcement, and on the other hand we have our cementitious composite. So we needed to establish what's going to be the depths of reinforcement, to find the neutral axis, and furthermore the cross-sectional area that we need to reinforce that. And finally, based on that reinforcement ratio for a balanced case, we also studied two different reinforcement ratios in order to optimize the ratio of reinforcement based on the cross-sectional area to further work on the architecture, macro architecture. And the reason to do that was to be able to stick to a consistent reinforcement ratio for different architectures, which was very important to us. For the preliminary tests on our simply reinforced longitudinal 3D printed reinforcement concrete, we used a simple 3-point bending accompanied by DIC in order to capture low displacement. And furthermore, we basically initially observed that the addition of reinforcement in general can, of course, improve the mechanical, the flexural properties drastically. As you can see, we are getting more load and also more midpoint deflection and a higher area under the curve. But in our study on different reinforcement ratios, we found out that this is the main load displacement behavior that we see in all of the samples. So we first have this initial crack, and after the load drops, we again get a load recovery in all of the samples. But in samples that had the lowest ratio, the reinforcement actually at the end ruptures, and we have a catastrophic failure. Whereas in samples with a higher ratio, especially the one with the highest, we get a more we get to a plateau where the sample gets into a more stable condition. So we showed that this can improve ductility, this can enhance the flexural strength, and based on that, we had to adjust the reinforcement ratio that we initially calculated using theoretical equations. So after establishing this, we kind of stuck into this reinforcement ratio for the rest of the parametric studies on different architectures. So next, as promised before, we started studying the macro architectures, and again we went to look into architectures in nature that could provide that mechanical advantage, cellular architectures in nature that have abilities such as good impact resistance, compression, and also providing a lightweight structure. And based on that, we decided to design cellular architectures, and cellular here refers to architectures that have cell units that are perpendicular to the loading in this case, and also perpendicular to the tension that the material is going to carry later. And another category that we decided to go with were the hollow architectures found in nature, such as in plant of stems, and these single or doubly hollowed structures could provide that increased area moment of inertia. And in this case, the hollow tubes are actually in line with the tensile stress and the loading that is going to be applied under flexure. So the final two pictures you see is where we actually start 3D printing our structures based on these designs, and finally we came up with 3 different architectures for our cellular category and 2 different for our hollow. And for our hollow, basically the difference between hollow bar and plant stem was the fact that in plant stem we had a secondary hollow architecture that was presented in the previous photo. So we had some design constraint to keep everything consistent throughout. So we kept the cover of our reinforcement consistent and also the reinforcement ratio. And we just wanted to study how these different architectures can help or change the overall flexural behavior. So the design, manufacturing, casting process was basically the same as before. First, we came up with the CAD design based on our constraints. Then we, using Slicer, we were able to 3D print these. And finally, we cast them. So this was not a 3D printing of cementitious composite. This was a cast concrete, but we used 3D printing for the reinforcement. And again, we went back to our 3-point bending test in order to capture the flexural behavior. And the initial results that we were able to see from our cellular samples showed that we are getting some increase in terms of the load and also the deflection compared to plain samples shown in black. But another interesting point was that the Kagami architecture here, which contained triangular unit cells, was actually showing a less catastrophic failure at the end, and it had a smoother drop in the load. Again, they were following the same pattern of initial crack and the load recovery, but in two cases of our cellular architectures, we had the rupture of reinforcement. On the other hand, in hollow architectures, we saw that initial crack again and the load recovery. We saw an improve in terms of the ductility, not that much in terms of load, when we added the secondary level of hollow tubes. And in general, although the reinforcement with rupture at the end, they showed a better mechanical properties than the cellular category. So as an example of the failure mechanism, so first when the initial crack happened because of the tensile failure in the matrix, next when the stress is transferred to our polymeric element here, we get that recovery until at the end the polymeric component also fails and we have the final failure of the whole composite. So based on this, we went back and looked at the different crack patterns that we're seeing, where in the case of the Kagami, one of the cellulars, we did not have reinforcement rupture, but the main reason of failure, sharp failure at the end, was actually because of failure at the cover, which we got from many of our samples in cellular. On the other hand, in single hull bar, the interface between the two could be better based on just these results, that we had to go further and look at the interface using some microphotography and later X-ray CT. So as an example of how we were observing these cracks or micro cracks within our structure, but we didn't have access to what's happening inside. That's why we were more curious about what if we use X-ray CT to see what's actually happening inside the reinforced cellular architectures. And as you can see, these are basically photographs that we could get from the outside and what's happening from the outside when failure happens. In order to do that, with the help of our friends at Princeton University, we were able to do some X-ray microscopy, and we observed that in different cellular structures, the failure is usually happening at the interface of these unit cells and our cementitious matrix, and it follows the crack path at the middle part of the beam. So this is what we also observed in another type of macroarchitecture that we have here, Kagami. But the difference with the previous one is that the crack actually followed a more complicated path, which can actually explain why we were getting more area under the curve with this one. And for the sample that was SNS, the main failure that we observed was again at the interface, but this time perpendicular to the loading. And this showed that actually because of less number of unit cells that we have, we are getting a very weak bond behavior between these two, and this form of failure is mostly delamination of the matrix rather than failure at interface. So going back to the data that we got from the Flexural tests, comparing the cellular and hollow with the plane, we see that we get an increase in both modulus of rupture and toughness. And overall, hollow architectures were able to maintain a better flexural behavior than the cellular ones. In order to get an idea of why that is, and for continuing this research, we went with hollow and we started modeling them, which was presented earlier this morning. And the reason that we came up with the idea of integrating this hollow design with what we actually have in mechanics of materials-based design of reinforced concrete was to increase the moment of inertia through allocating material and basically moving the material further from the neutral axis. So this was the next part of this research which was presented. And to summarize, we were basically able to increase the tensile and flexural behavior of concrete through adding macro-architected polymeric elements. And this was done basically as a proof of concept that if we are able to 3D print any material to use as a enhanced version of reinforcement, the material that we're using is not going to matter. We just need to adjust and optimize our design criteria based on the material properties. So later on, if we are able to do the same architectural adventure with materials like steel, we could even get things that get properties that are comparable to that of reinforced concrete. So as I mentioned before, in introducing the hollow motives was the next part of this research. Another future prospect for this project was to incorporate the additive manufacturing of reinforcement and cementitious material at the same time, and finally identifying the potential of using these macro architectures as in lightweight structures, and finally investigating the long-term behavior. So once again, I want to thank my advisor, Dr. Farnam, and also our friends at